Hello, my name is Mateusz Jamrozy, and today in my talk I will tell about exploring the influence of interfacial hydrogen bonding on surface properties and foam stability in saponin mixtures. At the beginning, I would like to highlight the importance of biosurfactants. Pollution of water reservoirs with detergents leads to eutrophication, reducing the amount of water available for consumption. Synthetic detergents used in cleaning products, cosmetics, and fertilizers are not easily biodegradable. For this reason, safe and biodegradable alternatives must be developed immediately. Ideal surfactants must be surface active, foaming or emulsifying in low concentrations. In addition, they must be safe for humans and the environment and should be easy to remove from water. Natural biosurfactants are compounds of natural origin obtained by extraction from a wide range of plant species and even microorganisms and animals. Synthetic biosurfactants are produced by industrial processes through chemical synthesis. It was thought that until recently biosurfactants cannot be used to create stable and flexible foams, which parameters can be modulated and controlled. Uh, However, foams are widely present in the environment. For example, there are animal species that are capable of producing stable foam to protect their eggs in various environment conditions. As a base for our biosurfactants, we choose saponin because it's a surfactant and biologically active compound of plant origin. What is super important, it's biodegradable, making it safe for humans and environment. It's a compound capable of forming complexes with other biopolymers or chemical compounds through electrostatic interactions or hydrogen bonds. Saponin can be both a hydrogen bond donor and acceptor. In the present work, we aim to demonstrate that it's possible to use hydrogen bonds to form complexes between saponin and donor and acceptors of hydrogen bonds. The purpose of this is to increase the surface activity and forming capacity, allowing to reduce concentration of saponin in cosmetics applications like foams or emulsions. As the modulators of hydrogen bonds, we choose choline chloride, urea, and glycerin, uh, that are chemical compounds that are well known as hydrogen bond donors and acceptors. What is worth noting, saponins are produced enzymatically from a variety of biological extracts, and their production and the number of subsequent extracts undergoing different types of transformation and biosynthesis. But our research is the next step to make the most efficient use of saponin in commercial applications. Now let's move to the sorry. Let's move to the experimental part of our study. One of the fundamental studies on surfactant solutions is the measurement of surface tension. Because ability of surfactant compounds to lower the surface tension by absorbing their molecules on gas-liquid interface uh, uh, is uh, is crucial in foaming processes and is directly related to the detergent capacity of the compound. These are two key parameters against which surfactants can be compared. Surface tension was measured using the pendant drop method. In addition, by including oscillations of the pendant droplet after around 3 hours of absorption, we are able to, via Fourier transformation, to study the viscoelasticity of the surface. Measurement of the surface tension of some saponin solution showed that saponin at the concentration of 0.1 gram per liter reduced the surface tension of water from a value of 72.4 millionewtons per meter to a value of approximately 38 millionewtons per meter by adsorption at the interface, what is shown on the first graph of the slide. Analysis of the results obtained for a mixture of saponin with additional compounds showed that the greatest effect of lowering the surface tension occurs for the solution containing the choline chloride additive. Choline chloride at the concentration of 1 mole in the tested solution caused a reduction of surface tension of to a level of 40 millinewtons per meter, which is also shown on the first graph. Moreover, increasing the concentration of choline chloride in the solution to 2 mole resulted in decrease in surface tension by a further 2 millinewtons per meter, with what you can see on the graph in the middle. As can be seen, the effect of large reduction of surface tension obtained for mixture slide. Let's move to the next test. The results of the surface viscosity measurements carried out the saponin solutions and the additives like urea, choline chloride, and glycerin showed that choline chloride and glycerin caused a decrease in viscosity of the tested solutions relative to the saponin in low frequency range. Only the addition of urea at the concentration of 1 mole did not significantly affect the surface viscosity of saponin. You can see the black and blue lines on the first graph. The effect of decreasing the value of this parameter was only observed when the concentration of this compound was increased to 2 mole, which is shown on the next graph. The introducing of additional compounds such as choline chloride and glycerin into the solution decreased the surface viscosity relative to saponin and urea concentration. In the next stage, we try to compare these measured parameters with foaming properties. In the next stage of the research we carried out was forming tests. We made tests using a foam column. The measurement was based on the foaming, the biosurfactant solution in the foam column with a filter on the bottom, through which the air was pumped. The measurement was carried out using an Antorpar foam analyzer shown on the right. Analysis of the results showed that the foam with the greatest stability was obtained from a solution of saponin and glycerin. The addition of glycerin caused the foam to maintain the greatest height throughout the test time. The reason for this high stability of the foam containing glycerin is most likely due to much higher surface elasticity value than for the other compounds tested. The addition of choline chloride also had a positive effect on the foam height. In addition, analysis of the results of the multi-component mixtures proved that additives such as choline chloride and urea significantly reduce the saponin, the stability of the foams obtained on the basis of saponin and glycerin. In the next step, the stability and evolution of foam was investigated by using a multiple light scattering technique with a multi-scan MS-20. analyzer. During the measurement, the measured values are transmission and backscattering, which allow to analyze a forum parameters such as foam height and the distribution of bubble size. The foam based on the saponin and glycerin solution showed significantly higher stability, independent of duration, and maintained a higher height after 15 and 60 minutes compared to the other foams. The transmission spectra showed on these graphs shows that each of the additives affects the clarity of the solution, with the saponin and urea solution recovering clarity is the longest, which can be seen on the first graph. A comparison of the results of the individual samples, such as a function of time, confirms that the processes that cause foam to fall occur most rapidly in the saponin and urea-based system. The backscattering values for this system, despite being similar to other systems tested. Immediately after foam formation, reach significantly lower values after 60 minutes, similar to the pure saponin-based foam. Let's move to a short summary. Based on the study, it can be concluded that the development solutions show application potential as modern biosurfactants with controlled physicochemical properties. Surface tension measured showed that choline chloride had the greatest effect on lowering the surface tension of the saponin solution, while urea and glycerin had a much smaller effect on the value of this parameter. The surface viscosity results proved that choline chloride and glycerin reduce the surface viscosity in the low frequency range. Analysis of the surface elasticity results showed that glycerin contributed to a significant increase in the elasticity of tested saponin-based solutions. It was also proven that glycerin increased the stability of obtained foams, while the addition of urea contributed to accelerating the foam processes like coalescence or coarsening. On the basis of the present conclusions, it can be stated that it's possible to use hydrogen bonds to form complexes between saponin and other chemical compounds.
Thank you very much.
Thank you very much.